In this segment, we will explore the physics in relation to a basketball shot.
Baron Davis. That'll be counted on a shot attempt. Oh! It's gotta go! It counted! It's good! Baron Davis has just put it in from 92 feet away.
An ideal shot requires a good angle to project the ball, along with sufficient force to give the ball the correct amount of kinetic energy to be placed in the hoop, and to give the ball a good backspin. Although recent study shows that a bank shot may yield a greater chance of the ball falling through the hoop, it is common practice to aim for the center of the rim and further away from the basket, as the target is constant regardless of where you are on the basketball court, and of course for aesthetic reasons. Putting a backwards rotation on the ball makes its trajectory more stable and more prone to bounce back into the hoop upon contact with the rim and or backboard, as the ball will encounter more friction, resulting in a smaller vector in the opposite direction upon collision. The proper technique is to flick your wrist straight as possible, which will make the ball spin throughout its flight. Next, let's take a look at the forces and energy in action during the shot process. At the instantaneous moment before the ball is released, the forces on the ball is gravity pulling it downwards, and the force of the shooter's hand pushing the ball diagonally are both in the horizontal and vertical directions. Potential energy is both stored in the form of gravity and in the person about to shoot the ball into the air, thusly putting work into the ball. As soon as the ball is released, several forces will act upon this object, such as gravity continuing to pull the ball down, drag pulling the ball down and backwards, the Magnus effect, which results from variances in air pressure because of the ball's spin, which will slightly increase the velocity in both linear and angular orientations. However, the latter two forces will not be considered in this project, but nonetheless are crucial factors in regards to the total precision of long-distance shots. Here is how the energy gets transferred during the flight. The initial energy from the person is transferred into kinetic energy in all directions, as well as rotational energy. Disregarding air resistance, we can say that horizontal motion and rotation energy will remain constant unless acted upon by another force according to Newton's first law. The vertical kinematic energy is inversely proportional to the energy due to gravity. If the ball doesn't go directly through the net, it may make contact with the rim and or backboard. In this example, the rim exhibits an equal and opposite force according to the component of force of the ball hitting the rim. The ball compresses at the instant it hits the rim, transferring some of the energy into the ball's spring action, which is then translated back into kinetic energy that results in the ball rebounding in a certain more complex trajectory. Each time the ball comes in contact with an object, some of the energy may be absorbed and dissipated in the form of sound and the erosion of the basketball's material. For example, the equation for projectile motion is 1/2 acceleration times time squared plus the initial component for velocity times sine theta times time plus the initial height. We know acceleration due to gravity is negative 9.8 meters per second squared. The velocity is the component of initial velocity in both x and y directions, which can be obtained with motion analysis software such as LoggerPro. Theta is the angle at which the ball is released, and y initial is the initial height at which the ball is released. Longer shots are tougher to make for several reasons. A longer distance will require more force, obviously, resulting in a larger spring action upon collision, making the ball less likely to go in. Compromise shooting technique, as the more successful flick shot is not practical for extra long distance shots. More kinetic energy can be stored into the ball if thrown from the chest or with the whole arm like a shot put. In turn, the ball will have less backspin and possibly more rotation along the Z and Y axis. Because of this, the Magnus effect has a greater precedence in conjunction with ball side spin, which may be negligible in the case of shooting closer to the basket. Here's a digital representation of Kevin Love's record shot as of 2009. Given his initial velocity of 17.8 meters a second, a released angle of 40 degrees, and given that his release point off the ground is around 2.6 meters. To demonstrate the importance of precision in Kevin's shot, here's a calculated trajectory had his angle been adjusted by a couple degrees.